Okay. So what I wanted to talk about first was, kind of ML from a historical perspective, right? So machine learning really got its wings, sorry, this is hard to see, it got its wings in the 1950s, that's the x-axis. And it goes from the 1950 to 2016, and the y-axis is a guesstimate in terms of funding. Okay. So what I wanted to point out first is machine learning kind of was invented, if you will, in the 1950s. And then it had a couple peaks and valleys, right? These valleys in the 1970s and the late 1980s, these are called the Great AI Winters. And an interesting question to ask yourself is, do we see kind of the current growth cycle continuing indefinitely, or are we in for a third winter at some point? Okay, so that's an interesting question. And yeah, and it turns out so this is my personal view, but the winters tend to correspond when hype and the technology kind of become mismatched, right? So if you have a lot of enthusiasm, but the technology isn't mature yet, then you'll get disappointment in winters. That's just my personal take on this. One way to view this historical trend is to kind of differentiate machine learning traditions within the grand scheme of things. So we've talked a little bit about decision trees, and we'll return to this topic more. But decision trees and these algebraic kind of approaches to machine learning, we can describe these as being part of a symbolist tribe. And okay, and then there's also kind of the connectionist tribe, and that's the topic that I'm going to turn to today. They tend to advocate deep learning style solutions. And then finally, there's the Bayesian tribe, which are empirical acquisition and automated insights. This is kind of the research tradition there, is a very Bayesian statistical approach to machine learning. So you can kind of see these tribes in action on this history. So if you kind of look at, kind of color code the popularity of various tribes over time, you'll see that before the first winter, before the first and second winter, the purple symbolist tribe had dominance. But deep learning was kind of popular, got smushed in the 1970s by a Marvin Minsky book, and then got resurrected in the 1980s and really took off in the 2012s. That's the blue kind of explosion. So this is just one way to view kind of the tribes competing for resources, if you will, in the history of ML. Questions, comments?
What's the other groups?
Yeah, the red and yellow. This derives from a book, let's see, The Master Algorithm by Pedro Domingos. And the red and yellow correspond to less well-known tribes, the evolutionaries and the analogizers, but I won't get into. Okay, so I wanted to talk one slide about deep learning applications. So the reason why deep learning is such a predominant topic today is in the through the 2010s, we've had this competition called ImageNet. And the task of ImageNet is, given an image, can you classify it? Does it contain a dog or a cat, for example? And up to the 2011, we had an error rate of about 25%. And then convolutional neural networks were invented in 2012. And this technology reduced our error rate dramatically and continued to reduce our error rate dramatically until the 2015s, when convolutional neural networks actually exceeded the performance of humans. And you can kind of see this for yourself. If you try and compete against this ConvNet, you'll actually do worse. All right. In natural language, you can train neural networks to, for example, do machine translation. This is behind Google Translate. And another example is you can train neural networks to generate language. So at the very beginning of time, at the very beginning of training, a neural network will produce garbage. But if you train, it'll start producing speech that more and more resembles actual English until at the very end of your training, you're starting to get novel generation, right? So this is another application. All right. Okay, so evaluating deep learning. Okay, so this is my take. It should, but this tends to be the perception shared by many. Okay, so on the pros side, the advantages. Since 2012, deep learning has been outperforming traditional machine learning models in practically every task domain, with very few exceptions. If you want to achieve state-of-the-art, you will pay attention and train on these models, with a few exceptions. All right. So, and that's a big pro. All right. And there are the Python libraries that undergird deep learning technology, TensorFlow and Keras, and there are others. They tend to be very well supported and easy to use. There's a vibrant open source community, so if you want to solve a task, you just go to GitHub, you download a project, and you start modifying and extending it. And GPUs make the process of training, which has been traditionally extremely painful, a little bit more tolerable. All right, on the con side, deep learning is very data hungry. So to get good performance, you need millions of records. Its interpretability is very challenging in a deep learning context. It's possible to interpret what a deep learning model is doing, but more or less it can feel like a fancy oracle whose inner thoughts, inner beliefs are mysterious. All right. Another important criticism of deep learning is it's more of an engineering discipline than a scientific theory. It's reminiscent of kind of a Nikola Tesla style of find what works. And theoreticians, scientists are trying to play catch up and explain why deep learning is working. There's lots of enthusiasm, but that's also a con in that there's lots of hype. Okay, so really briefly, I wanted to kind of peek under the covers and show you how deep learning works from a mathematical perspective. So you guys know trend lines. Okay, trend lines. So trend lines, you guys are familiar with the structural component of trend lines specifically. So the structural component is the equation of the line. In this example, we have 2x plus 10. The slope is 2, the y-intercept is 10. Okay. There is a second component to trend lines, to regression, and that is the random component. So, and this is expressed in the belief that at every x value, you'll have a distribution of error. So you'll have most of your data points will reside close to your blue line. That's the peak of this bell curve. And then as you get further away, you get less likely to see data that's far away from your structural component. So there are two components of trend lines. Okay, Tableau only visualizes one. All right, fair enough. Okay, so in linear regression, the trick is that you take the value of y and you plug that in to the mean of the normal distribution. So the mean of these yellow bell curves, that equals the blue line. Okay. Okay, but we can generalize this. We can say, I'm going to plug in into my mean a function of y, which so in linear regression, the function is simply y. It's the identity function. So in linear regression, you get just what we've seen before. But if you make the link function, this g function here, nonlinear, you'll be able to create more complex and interesting models. For example, if you plug in this natural log sigmoid function, this is how you move from linear regression to logistic regression. But you don't have to use logistic regression. You don't have to use the natural log to do a link function. You can have any arbitrary link function that you want. For example, you can do something like a rectified linear unit that looks like this. So the choice of link function is basically choose what works and prove interesting properties of your given link function. So in general, I'll comment that neural networks started to use a link function like this, but they moved towards a link function that looks like this over time. That was one of the inventions in 2012. All right. Okay, so really briefly, so let's talk about perceptrons. Okay, so perceptron has a bunch of x values here, and you multiply these x values by the weights on the edges, and then you sum it. And then you take a thresholding operation. So this kind of graph, it corresponds to logistic regression. So what I'm going to show to you is that the blue stuff on this graph, that corresponds to the structural component. So the sum of of x times w, that is the structural component. And the link function, that is the thresholding operation. This is the nonlinearity, is the green thing on this graph. So the key insight, oh, and a comment is that the random component, the binomial distribution, which is tied to logistic regression, that's not directly represented on this graph necessarily. Okay, so the insight here is that if you look at logistic regression from a graphical perspective, when you have an input vector outputting to a single scalar prediction, this perceptron graph corresponds to logistic regression. That's the comment here. Okay. So what we see is that this perceptron graph right here, it corresponds to logistic regression. And what we want to do is we want to extend the perceptron, and that's how we invent neural networks. So the idea is instead, okay, so on the perceptron, if you flow from left to right, that's prediction. And you flow right to left, that's learning. Okay. All right, so to invent a neural network, all you do is instead of having one output neuron, you add a bunch. So you add another output neuron here, and you add a third and a fourth, and you basically have a vector of outputs. And then after this, you make another layer. So you have your final output over here. So you're adding layers is the key insight here. So you move from a perceptron to a neural network by adding these hidden layers. This is kind of a two-layer neural network, depending on how you choose to label things. But you can imagine these layers extending. There being 150 hidden layers, and that is the state that we're in. This is why it's called deep learning. Is the number of layers you have can be very deep, especially if you switch to conv nets. All right. So the idea here is we have a scatter plot. And we have three different regression models that we've trained against it. The red is a linear regression model. The blue is a polynomial regression model. And the green is what's called a non-parametric model. Okay, and we can kind of see in this particular data set, the green curve we tend to prefer it, right? Okay, let's explore why. So the way that parametric models work, this is kind of a hand-wavy kind of an explanation, but this is roughly how it works. So you assume a structural form. So in a linear trend line, right, you assume that your data lies on a line. And then after you make that assumption that your data lies on a line, you train your parameters, so that's step 2. And then on step 3, you validate that your trend line visually or empirically, whether your trend line actually lies on a line. This is how structural models tend to work. Okay, but we don't have to assume at the beginning of time that your data fits into a structural form like a line or a polynomial. You can use non-parametric models to, instead of assuming a structural form, your data is a line, you can learn that structural form more directly. But this non-parametric model, in exchange for this flexibility that you see exhibited up here, in exchange for that, non-parametric models tend to be less data efficient. There's less signal, there's less power in a non-parametric model. So we can kind of express the difference this way. A parametric model has a high degree of sample efficiency because it has this structural assumption, an inductive bias, if you're familiar with that term. But in exchange for high sample efficiency, it's less expressive. It's not able to capture data that doesn't fit in with your assumptions. A non-parametric model, in contrast, it's much more expressive, as we see in this scatter plot. It's better able to fit data like these. But in exchange, it's less sample efficient. So this distinction between parametric models and non-parametric models, it's familiar in statistical circles. The key insight I'll give to you, if you will, is that most models are parametric models that we'll talk about in this class. Deep learning and support vector machines, these tend to be more closely akin to non-parametric models. So when we see performance graphs like this, and which show that the neural networks do worse at low data, do better at large data. These kind of performance curves are an expression of this trade-off. The traditional machine learning, the red, it is that way because it's sample efficient, does well at low data, but it has less expressivity. Okay, so this is kind of the trade-off that I wanted to point to. We've got parametric, non-parametric, traditional machine learning, non-traditional machine learning. And that's my final slide.